Hi, boys and girls. It's Miss Messina here from Team Cortland.
Hi, boys and girls. It's Mrs. Viola from Team Geneseo.
Hi, it's Mrs. Levin from Team Purchase.
Hi, it's Mrs. Cabrera from Team Stony Brook.
Hi everyone, it's Miss Hidalgo from Team Geneseo.
Hi guys, it's Mr. Schwartz from Team Cortland.
So, boys and girls, this week we're going to be reviewing some concepts that might have been a little bit difficult because chemistry and density could be a little bit difficult at times. So just hang on. We're going to review with you a little bit. It's okay to be a little confused, but after we do a couple of activities with you this week, you're going to feel a whole lot better. All right, so here we go.
Let's start off with some review. So first up, hopefully you guys remember mass is the amount of matter or stuff that makes up an object. Volume is the amount of space an object takes up. And density tells us how compact the mass is in a particular substance. Gases or liquids tend to be less dense. Iron and things like hard rock tend to be more dense. And the less dense something is, the more it's going to rise above things that are more dense. So to calculate density, you absolutely need to know the mass and the volume of that particular substance. To find the mass, we would usually use a triple beam balance or an electric scale like the ones pictured here on the screen. If we have a solid, we can actually calculate that mathematically, like say for a cube, where we multiply the length, the width, and the height of that cube to find its volume. For a liquid, we would measure it out using a graduated cylinder or measuring cup like the one pictured here to calculate the volume of a liquid. And to find a mass, we're actually going to watch Miss Levin help us find the mass of different liquids and then calculate the density of water.
Now, is the density of different amounts of water always going to be the same? It is. So we want to measure the density of a liquid. So I have some liquid here, my measuring cup, and should I just pour it onto my triple beam balance? That doesn't sound like a good idea. So in order to find, I'm going to do 100 milliliters of water. So I'm going to measure this. I'm going to measure it exactly 100 milliliters. And we're going to measure the mass of 100 milliliters of water. So what should I do? Should I just put this on here? No, because that's measuring the graduated cylinder plus the mass. So I'm going to measure, I have to put it into an item. So I'm going to measure when it's exactly zeroed. I'm going to put this to the side. I'm going to measure a cup first because I'm going to put my 100 milliliters in the cup. 35.4 grams will be my container. Now I'm going to put the water in. I'm going to put in 100 milliliters of water. So now I have 135.3. So how much is the water here? Pretty close to 100 grams. So what's the density going to be? Simply take the mass and divide it by the volume. And in this case, it's equal to 100 grams divided by 100 milliliters, which for a liquid density comes out to 1 gram per milliliter, because we cross off the 100 off the top and off the bottom.
So thank you, Ms. Levin, for demonstrating to us that the density of water is 1 gram per milliliter.
So let's go over finding density of an object. So we remember that density is found by doing mass divided by volume. So here we have 2 cubes of the same volume but different masses. So to calculate the density and find out which one has the greater density, we would again do mass divided by volume. And that's why we're able to see that the cube with the greater mass, 25 grams, has a greater density of 2.5 grams per centimeters cubed compared to 1.5 grams per centimeter cubed. Now, what if we don't have the exact volume of particular substances? Well, then in that case, we're going to watch Ms. Schwartz demonstrate to us how we can figure out which object has a greater density when the only thing that we know about these objects is their masses.
All right, so today we're going to be looking at mass. So as you see on the screen, we have an electronic balance. And we're going to see how different size objects we could predict their mass, and then we could see how they do behave when they're compared to one another. All right, so I have the scale in front of me. And I also have here, this is a wax candle. And you can see, if I hold it up next to a piece of clay, they look as if they have different volumes. Saying that, the candle is larger than the clay. So we can predict, well, if the candle has a larger volume, how would the mass of the candle compare to the mass of the clay? So let's take the mass of the candle, which is larger first. And it reads as 10.8 grams. So the larger candle, meaning the candle that has a larger volume, has a mass of 10.9 grams. Now let's take the mass of the clay, which had a slightly smaller volume, 10.2. So which one was heavier? So the candle has a higher mass. So then we can make a prediction which one then would be more dense, meaning the amount of material in this given volume, which one would have their molecules closer together. Well, let's see how it behaves in a glass of water. I'm going to use the candle first that has a larger mass. I would think. And then compare it to the clay with a smaller mass. And we could observe that the one with a smaller mass sank, but the candle with the larger mass, larger volume, is floating in the water.
Thanks, Mr. Schwartz. So let's go over and see what's happening on a molecular level with these three different substances. First up, the wax candle. So wax is made up of carbon and hydrogen atoms that are bonded together in long chains, and you can see from the image on your left-hand side how there are spaces between those chains in the wax. In the center, we can see the water molecules, which are made up of oxygen and hydrogen, and we can see how those are more closely packed together. And finally, on the right-hand side, we can see clay, which has oxygen, silicon, and aluminum atoms, and we can see how they are packed even closer together than the water molecules.
All right, last question that I want you guys to think about, and that is, how do the densities of different liquids compare to the density of water? So we already determined with Ms. Levin that the density of water is 1 gram per milliliter. You already saw with Mrs. Schwartz how the densities of different solids compare with the density of water, right? We saw that with the candle wax and the clay. We noticed how the clay sunk to the bottom of the glass while the candle wax stayed floating, and that let us know right away that the density of the clay was greater than the density of water, but the density of the wax was less than the density of the water. So I'm going to share with you guys just this quick video that I found, and this will help us to figure out the answer to this question. How do the densities of different liquids compare to the density of water? So we have a cup that's being filled with water with some food dye, and now we're going to add some syrup to this cup. Add just a little bit more water, and finally add a nice layer of oil. All right, so what are some things that you're noticing here, right? Hopefully you notice just kind of the arrangement of these three different liquids, right? The syrup is down here at the bottom, the water is in the middle, and the oil's at the top. All right, so what can we say about the density of the syrup compared to the density of the water? Well, the density of the syrup is greater than the density of the water, and that's why it's sunk straight to the bottom. What can we say about the density of the oil compared to the density of the water? Well, the density of the oil is less than the density of the water, and that's why the oil stays at the top.